I'm really excited to have this opportunity to tell you about some of the work that we've been doing in my lab on lithium metal batteries. So to start off, I just want to give you a brief orientation on why we're so excited about batteries in my lab. So let's see if I can, there we go. So we're all pretty familiar with rechargeable lithium ion batteries. They power our cell phones and our laptops, so something that we carry on us each and every day. But more importantly, they're going to be a very important part of this climate revolution that we're looking forward to in the next few decades. So we're already starting to see lithium ion batteries power electric vehicles, like I'm showing down here on the left-hand side of the slide. And the sale of these vehicles is expected to explode over the next few decades. But even beyond things like electric vehicles that are going to play a critical role in mitigating greenhouse gas emissions, we're going to start to see things like clean urban buildings, lithium ion batteries interfacing with our electrical grid, and reducing CO2 emissions that way by allowing things like renewable energy from the sun or the wind to actually come online and power our buildings that we live and work in every day. Lithium ion batteries are also likely going to play an important role in medicine, both in the way that we treat disease as well as the way that we eat food. But they're also going to play an important role in artificial intelligence by powering these little robots we have in our house, and that we're going to see more and more of in the future. So what actually is a lithium ion battery and how does it work? So traditional lithium ion batteries work by this principle called intercalation, where you have lithium ions floating around an electrolyte, and then you have an anode, so the negative side of the battery, and a cathode, which is the positive side of the battery. And you can charge the battery, which means you move lithium ions into the anode side, or discharge the battery, which is what happens whenever you're actually using your cell phone, for example. And the lithium ions, they move from the anode side into the cathode side of the battery. So whenever you do something like use your cell phone, you have lithium ions moving from negative to positive, and this is accompanied with the movement of an electrical current that actually powers a load. And in the example I'm talking about right now, that load would be your cell phone. So you can look at individual apps. But the load in the future is also going to be an electric vehicle, or it's actually going to be, powering your television at your house, because it's going to be how you actually get electricity in the first place. So why are we actually devoting so much of our time and energy to researching lithium ion batteries? They've been around forever, so they've been around since the 80s. We use them every single day, but they still have lots of issues. So this entire image here is dedicated to showing what exactly happens when this intercalation process doesn't go exactly as intended. So you can have a bunch of different types of failure in the battery that cause serious safety concerns, such as these fires and these very famous safety incidents that have been covered in the media. So you can have something like a battery puncture or mechanically crushing your battery that leads to a fire in an electric vehicle, for example, which is obviously worst case scenario. You never want the vehicle that you're driving to spontaneously catch on fire. You can also have a scenario where the battery gets overcharged, which is what I'm showing here with these hoverboards. So this was back in 2016, where there was several instances of hoverboards spontaneously lighting on fire, sometimes while people were riding on them. This is due to the batteries charging at the incorrect charging rate. And whenever you do that, you end up not intercalating the lithium ions into the anode, but rather plating metallic lithium on the surface of the anode, which is how you get into this abuse scenario and thermal runaway. And we'll talk a little bit more about that. You can also just have an internal short circuit, which is where you have your negative and your positive side of the battery, and they're separated by a physical polymer separator in a traditional lithium ion battery. But if those two pieces of the battery touch each other, the battery short circuits, the cell dies, but it can also, again, go into thermal runaway and your device can catch on fire. And this is the famous Boeing incident. So you can, after this talk, you can Google this and you can see the fire that actually happened on the plane. Batteries in general, if they're not operated at the proper temperature, they can just start to overheat. So this can happen because the battery is physically at a higher temperature, or this can happen because you're charging at an improper rate. And that will also heat up the battery as well, similar to the overcharge scenario that I talked about before. Again, this causes the system to go into a situation of thermal runaway where the entire device can just spontaneously light on fire. The other issue with these batteries lighting on fire is that lithium itself is pretty reactive. If you look at where it falls on the periodic table, lithium metal is a pyrophoric material. So whenever these things catch on fire, they're around a lot of organic electrolyte. It's a pyrophoric material, and the fire doesn't actually behave like a normal fire. So they're actually very hard to put out. Even if you do get the fire put out, it can spontaneously reignite, and they burn at a much hotter temperature than a normal electrical fire, say. So it actually poses a great risk to the people who have to put these fires out, so the firefighters, and we'll talk a little bit about that as well. So what is actually going on whenever you have these scenarios of thermal runaway, and how do we start to study this a little bit better, and what does this mean in a real life scenario? So this is, again, just showing a schematic of a lithium ion battery. So whenever you do something like charge a battery too fast, I told you that you can get lithium metal plating on the anode side of the battery instead of intercalating into that inner layer space. So this is just a cartoon showing lithium metal that's deposited on the surface of an anode. And lithium metal, whenever it's depositing, it tends to grow in these wiry dendrite-like structures that I'm showing here. Whenever it grows in these dendritic-like structures, they are very sharp and they can pierce the separator. And what that means is whenever they pierce the separators, that they can cross over, connect to the positive electrode, and cause a short circuit. That obviously causes the cell to die. So this is no longer a functioning battery if you don't have a separation of voltage between the positive and the negative side. But another thing that happens is you'll notice in this cartoon, I have it drawn with a very high surface area. So this lithium is very fluffy on the surface. So what that means is that's a lot of surface area for decomposition reactions from the electrolyte to start taking place on the surface of this lithium metal. And obviously these dendritic-like structures have high surface area as well. So if the cell is starting to heat up, you have more decomposition that's occurring. You have lots of surface area for it to occur on. So it's basically just the perfect scenario for thermal runaway to start to occur once you have this dendritic or microstructural lithium start to grow in your cell. So this is really what we're sort of interested in studying in my lab. So how does this pop up in real life? Is this something we should really be concerned about? And the answer is definitely yes. We're going to have to be concerned about it. So I told you a couple scenarios that have been in the media. This is certainly the most recent one. So this is the Arizona Public Service battery fire. So this happened last year, and they just released the investigation report on what happened with this battery fire. So this is a very large battery center for grid storage. So this means that this is basically a whole bunch of lithium ion batteries stacked together, and they supply power to the electrical grid in Arizona. What happened was there was suddenly a major fire and a major explosion in one of these modules. So after the fire, it was so powerful that this side door of where the batteries were stored was completely ejected off. So these are images from the aftermath. This is what the building originally looked like with the door intact. This is after the lithium ion batteries caught on fire. So I told you they burn much hotter and they can cause explosions. So it blew this door off. This is the rear of the trailer where the batteries were stored. You can see it also ejected the rear door. There's debris all over the ground that basically flew out from where the batteries were also stored. So let's take a look inside. This is the culprit. So this is where the faulty battery was found. So you can see this entire module was burned to pieces. This is what it started off looking like. And this is what caused that severe explosion. So whenever they took the batteries out of here and they disassembled them, what they actually found inside were these lithium deposits. So this is what the microstructural lithium that I told you about actually looks like in a real life battery that does cause a serious safety hazard looks like. So whenever this fire was being addressed, 4 firefighters were injured. They all survived and made a full recovery. But these fires are extremely dangerous, and it all basically starts from this microstructural lithium. So let's talk a little bit about why this microstructural lithium forms, what we can do to stop it, and some of the things that we've really learned about it. So this is a diagram showing how a lithium ion battery essentially operates. So you have your anode, which in our case is lithium metal, and then you have some cathode material. So this is just a common example, but this could really be any type of material. And this x-axis here is just showing the voltage difference between these two materials. So lithium metal or graphite, which is more commonly used in commercial ion batteries, lithium ion batteries, shows up somewhere around 0 volts. And then you have your cathode material that's going to show up somewhere around 4.2 to 4.5 volts up here. So you have this separation in the potential between your anode and your cathode, and that's what allows the battery to function in the first place. The main issue with all batteries is that the electrolyte that you use is suspended in this carbonate solvent. And this carbonate solvent is not electrochemically stable at the operating potentials of your anode or your cathode. So what I'm showing here is basically the window in which the carbonate electrolyte that's used in commercial lithium ion batteries is stable to operate in. So you can see it has a lower cutoff voltage of about 1 volt. So what this means is that when you start operating the battery at low voltage, is that you have decomposition of this electrolyte material, and it forms something called the solid electrolyte interphase on the surface of lithium metal. The structure and the composition of this decomposition layer is what we think is actually dictating this microstructural growth that can sometimes grow out of control and cause these very serious safety concerns. We think that ethers might be one promising way to stop this microstructural growth because it has a better stability window at lower voltage. And I'll talk a little bit about that in the second half of my talk. But basically, what we want to know is how can we change this electrolyte formulation to change lithium microstructural growth in a battery and make them safer. So the main hypothesis behind all of this work is that you have some electrolyte And as soon as you dip your lithium metal into the electrolyte, you form some type of solid electrolyte interphase layer, this SEI. This can be a good SEI or this can be a bad SEI. If this is a bad SEI, whenever you start plating lithium on the surface, you get this dendritic-like growth that could pierce the separator and cause your cell to short circuit and light on fire. If you have a good SEI, what would happen is you get these lower surface area structures that are more flat on the surface. So they're not going to jet off and pierce the separator at any point during battery operation. So whenever you start plating lithium on the surface, it's very smooth. And when you take it away during discharge, it's also very smooth. So it's basically, if you have a good electrolyte, it's a very reversible process. If you have a bad electrolyte, this process becomes very irreversible. You also see things like a loss of efficiency in the battery. So when you have these dendritic structures and you try to remove the lithium from this, so you try to strip it back off and get this lithium back out during discharge so that you can make this battery rechargeable, it actually doesn't work so well. So it doesn't want to come out in a homogeneous manner if the SEI isn't very good. And so you end up getting these chunks of lithium that are actually separated from your original anode. And this is called electrochemically inactive lithium. And this is what's going to lower the efficiency of the battery. So if we have a scenario like this after stripping and we go to plate more lithium again, it's not going to plate here, it'll plate here, but now all this lithium is lost and we can't use it to do a reversible reaction anymore. So this scenario is bad for many reasons. So how do we actually go about figuring out how any of this stuff works? So our favorite tool to use in my lab is something called nuclear magnetic resonance. It's very similar to an MRI that you could get at a hospital. But instead of always looking at an image, we can also look at the spectroscopic signal of individual molecules that are on the surface of these lithium metal anodes. We can also still take an image. So this is actually showing a lithium cell where we have just two strips of lithium, and we've grown some dendrites to connect them together and intentionally short circuit the cell. This is showing a spectrum of what we get and the type of chemical resolution that we can get, so we can really assign, what are these chemical species, what are these electrolyte decomposition products that form on the surface of our lithium metal, so that we can actually correlate electrolyte decomposition with lithium microstructural growth that we see in the cell. We can also start to learn about how lithium ions move through this layer. Because with NMR, we can not only look at structure, but we can also look at dynamics. So we can assign all of the chemistry that's on the surface of lithium metal, and then also take a look at how lithium ions are actually being transported through here. So we can really provide a lot of molecular level insight into how these microstructures form, why they form, and how we can prevent their formation in the first place. So one of the first projects that we started to work on in my lab is, are there some type of additive that we can put into just a conventional commercial carbonate electrolyte that would give us smoother lithium deposition? So anything we could throw in there that would make the battery a little bit safer. So this is actually showing these microstructures that grow on the surface of a lithium metal anode. Just depositing in a conventional commercial lithium ion battery electrolyte. So that's what I'm showing here on the very far left. So you can see that whenever we do this experiment, we get these high surface area structures. Some of them look very pointy. So if we continued to grow, maybe they would grow and pierce the separator. So it doesn't look like a very good scenario here, which is consistent with what we know. If you push conventional carbonate electrolytes too hard, then you end up getting these sharp dendritic growths. So what we tried to do was see, could we add in some, say, potassium ions in very, very small concentrations and improve this deposition morphology. So what we see is that if we add in a little bit of potassium, so zero 0.1 molar potassium to a 1 molar lithium electrolyte, it starts to get a little bit smoother. Still some high surface area structures in here. But if we add 0.15 molar, we end up getting these large areas of smooth lithium deposition that are much more favorable and more safe for the battery. So this tells us that something is happening to the electrolyte decomposition at this concentration of KPF6 that mitigates lithium microstructural growth. So what's actually going on here? How is the electrolyte decomposition different in these two solutions? So we take a look at the solution NMR after extended cycling in the battery. And what we see is that when we have KPF6 present in our electrolyte, we actually have much smaller amounts of these soluble electrolyte decomposition products. So these short chain alkyl carbonates are not as present in the electrolyte. And then when we have KPF6, we also have a different ratio of these polycarbonates and polyethylene oxide polymers in the solid phase that's attached to the lithium metal surface that is probably changing the ionic conductivity to the lithium metal electrode. We also don't see any of this lithium carbonate material. And lithium carbonate is known to be a poor ion conductor. So in a way, it sort of blocks lithium ion transport to the lithium metal surface. So what this is basically telling us is that when we have KPF6 present, we don't have as many soluble electrolyte decomposition products, and we have more ionically conductive species in this SEI layer, which is probably helping our lithium ion transport to the surface of the anode. So this is sort of a cartoon picture of how we think these SEIs are different. So overall, we have less decomposition whenever we have KPF6 present. So we have a thinner layer here. It's probably helping us get better ion transport to the surface. There's not as much gunk to sort of wade through for the lithium ions whenever they're trying to be deposited. And we think that this helps us get better deposition behavior. So we were really excited by this result, mostly because it's a completely new way to tune the SEI. So what battery manufacturers do in industry is they add these special carbonate molecules to the electrolyte. And so this is fluoroethylene carbonate and phenylene carbonate. And what these do is these preferentially decompose over the other carbonates that are in solution, and they form these branch chain polymers in the SEI. Supposedly, these branch chain polymers offer better mechanical properties in the SEI, and this is a very active field of study. But what this is showing us and what our work is showing us is that these alkali metal additives might be a completely new way to tune the SEI. So instead of adding something to the SEI, what we're doing is we're intentionally taking it away. So we're not forming lithium carbonate, and we're not forming these soluble alkyl carbonates that seem to be detrimental for lithium ion battery performance. So that was very fun and interesting to us, and we were excited by that. So we wanted to see, could we do this in maybe another solvent system? So another popular solvent system for lithium metal batteries are these ether solvents. So I showed you on one of the earlier slides that ethers are much more stable at lower potentials. So they should lead to better lithium deposition behavior. They shouldn't decompose as much, and you should get a better SEI. But what actually happens in practice? So what the black and the blue squares and data points here are showing is an ether-based solvent with a standard lithium salt. And what we see is that whenever we look at the Coulombic efficiency as a function of cycle numbers, that it seems pretty good to start off with, but then it quickly falls off and becomes very scattered because the battery is likely starting to short circuit. The performance is not very good. If we take a look at the SEM images over here, we see again, we get these high surface area structures. So it tells us that, you know, we still have something that's pretty unfavorable in our SEI that's causing these dendritic structures to form on the surface of our lithium metal. But if we change up our salt composition a little bit and we add about 50% of this original salt, this lithium TFSI, and 50% lithium nitrate, it completely changes the game. So we get these very low surface area structures that don't show any sharp features, and we get very high Coulombic efficiency. So we're right around 98% for 100 cycles, which is very impressive for a battery electrolyte. So what's the difference? So what is this nitrate doing in our electrolyte? How's it changing our electrolyte decomposition pathway compared to the normal TFSI sample? So again, you'll remember, in general, the solvent should be very stable, especially compared to the carbonates. So we wouldn't necessarily expect the solvent to decompose. It might be that the salt itself is playing a more important role here, especially since we see big changes whenever we add a different salt in. So if we take a look at our proton NMR, so this is just showing changes in decomposition of the ether molecules after extended electrochemical cycling. What we see if we compare to the pristine mixture is that we don't really see very much decomposition in the ethers. And that's pretty consistent with what we would expect given the electrochemical stability. So these are the specific ether molecules that we have, this DOL and this DME. We see a wee little bit of lithium formate formed in the TFSI sample, but it's so small, you can't even see it in this spectrum at its original magnitude, showing the DOL and the DME. I had to blow it up and show it in this inset here. So very minuscule amounts. We don't see any of this in the case where the nitrate is present. However, if we take a look at the fluorine spectra, where we only have fluorine on our salt here, so our TFSI has these CF3 groups on either side, we do see differences in our salt decomposition when we have lithium nitrate present versus when we do not. So this is the spectral signature that we get for TFSI, just in its original state. And then in blue, I'm showing 1 molar LiTFSI after 100 cycles. And then I'm showing 50-50 TFSI lithium nitrate after 100 cycles. So in both cases, you get these little mini decomposition peaks out here. But what's most noticeable is that you get these larger decomposition peaks that are fragments of this CF3 from the TFSI that are highlighted here. So this is quite a high concentration of salt decomposition product when you don't have any lithium nitrate present. And we know that the performance and the pleating behavior is much worse in this electrolyte here. So what's actually deposited? So that's what's happening in solution. What's actually deposited on the surface of these lithium metal anodes? So if we take a look at the carbon-containing species, we see something that's really interesting. We actually see that we have more of these polyethylene oxide type polymers when we have the nitrate present, and we see more lithium fluoride when we have the nitrate present. So this is very weird, especially given what I've just told you about the KPF6 additive case in the carbonate electrolyte. Because what this means is that when we have nitrate present, we actually have a much thicker SEI. But what that's telling us is that it actually isn't always a bad thing to have a thicker SEI. So like maybe this isn't totally goop that the lithium ions have to swim through in order to get to the lithium metal anode. Maybe what matters most is having less soluble decomposition products and instead optimizing the composition of this layer. So if we have something that is highly conductive to lithium ions, it's basically like having a rapid that's pushing you down the river towards lithium metal, whereas this might be like wading through a mud pole. So one case, the thick SEI is bad because it's made of stuff that's not conducive to getting you towards the lithium metal surface. But in this case, it's actually helping you get there because what's comprising it here is highly conductive to lithium ions. So we were very intrigued by this idea and we wanted to test this hypothesis. So we had to come up with a way to actually measure lithium ion diffusion through this layer and compare it to the case with just the TFSI. So like I told you in the beginning, the very beautiful thing about NMR is that you can measure both structure and dynamics. So here we're interested in measuring the dynamics of the lithium ions. So if we take a look at our lithium NMR, just as is, we end up getting this one singular peak sort of around 0 ppm. We see our lithium metal peak around 250 ppm, but I'm cutting that off for now. I'll show it to you later. So this doesn't look like we have a high diversity of things in our SEI. It just looks like we really have one thing. So, but we know from our solid state NMR that we likely have lithium fluoride, we have lithium near organic species, lithium metal always has an oxide layer on it. So we need to come up with some way to deconvolute this peak to assign all those individual species. So what we do in this experiment is we play a little game and we pass magnetization between different atoms in this experiment. So we can pass magnetization from our fluorines to our lithiums to see which region of this spectrum corresponds to lithium fluoride. We can pass magnetization from our protons to our lithiums to see which region is lithiums near the organic components. And we can also just assign, where does lithium oxide show up here? So if we do that type of experiment, what we end up getting is these spectra shown here in different colors. So this yellow spectrum here is a spectrum that we acquired by passing magnetization from fluorine to lithium. So this is probably lithium fluoride, probably some residual TFSI. Then we have this, what I'm calling LIR. So R just meaning any organic group, but we've acquired this spectrum by passing magnetization from protons to lithiums. So you can see it sort of falls in the middle. And this blue spectrum here is the spectrum that we measured for lithium oxide. So you can see that all of these different regions of this black lithium envelope correspond to different lithium species. And we can see how lithium ions diffuse in lithium oxide, organic lithium compounds, and lithium fluoride to see, where's the bottleneck here in the SEI. So the way that we do that is we use an experiment called EXE. So it stands for exchange spectroscopy. And you can run it in such a way that you see exchange between things in the SEI. And that's what this big blob here is showing. So I'll walk you through this. This blob here is showing lithium metal. So this shows up around 265. So this diagonal shows just a simple NMR spectrum where we see our SEI that I just showed you on the previous slide, and we can assign the same color coordination where we have our lithium fluoride, our organic lithium species, and our lithium oxide. And then we have our lithium metal further downstream. Sorry, my phone is ringing. But then we also have these things called cross peaks, where you see this cross peak here, and it comes in at a chemical shift that matches with lithium metal in the SEI. And then we also have this cross peak here that that matches up with lithium metal and the SEI. So you can see the center of mass is sort of over this lithium oxide peak, which tells us that lithium ions are exchanging between lithium metal and the passivating lithium oxide layer that's just naturally on the surface of all lithium metal because it's so reactive. We also get directionality from this experiment. So this cross peak indicates lithium ions that are moving from the SEI to lithium metal. This one indicates lithium ions that are moving from lithium metal to the SEI. And then actually we can zoom in even further and take a look at this blob and see, how is lithium oxide exchanging with lithium fluoride by zooming in on this region, for example. And we can start to pinpoint all of these different diffusion coefficients over these individual interfaces. So this is what the data looks like whenever we actually look at the decay. So how we run this experiment is we vary the time that we let our lithium ions diffuse in the experiment, and then we can fit that to extract our diffusion coefficient. So what you'll see, just all you have to take away from this data is that if something decays more quickly, then it has a faster diffusion coefficient. These little X's here are all for the nitrate containing sample. So you can see for every single SEI component, we get faster lithium ion diffusion whenever we have the nitrate present. So that tells us something about the mechanism of what the nitrate is doing. It's helping lithium ion conduction through the SEI. So what are these actual diffusion coefficients? So what we see here is the individual diffusion coefficients for lithium fluoride going to other places in the SEI and so on. So this is sort of a lot of data, but just to summarize what we see, and the most important parts here is that lithium atoms moving to the passivating lithium oxide layer, they all have the same exact diffusion coefficient. So that process, that dynamic process at that electrode SEI interface is not changing whenever we change our electrolyte. What seems to actually be changing the most is the layer above that, when you're going from lithium oxide to the rest of the SEI. So that process is very fast when you have lithium nitrate present, and it's much more slow whenever you have only TFSI present. So what that tells us is something happens whenever you have lithium nitrate reduction. It likely forms some nitrate reduction products that deposit near the oxide interface that improve lithium ion conduction there. And we think this is really cool and interesting. So we can sort of assign, we have these new decomposition products in our SEI, and it's sort of like a Google roadmap for us. So we can tell ourselves, if we use this TFSI electrolyte here, we're going to be taking this route where there's some roadblocks, and we know exactly where they are. We know the molecular structures that are causing them. If we use this electrolyte that combines TFSI and lithium nitrate, we're going to take this other route where it's much smoother. We're going to get there more quickly because we have better conduction through this SEI layer. So that's essentially where we are right now. Some of the things that we're learning about how to improve lithium deposition, these things that we're learning about how lithium ions move through this layer seem to correlate with improved lithium plating. So it seems like it's a very promising route to make safer batteries. So we're really excited about some of these new avenues to continue to study. So with that, I'll thank my group. So most of this work was carried out by my PhD student, Richard. He's done tons of work looking at lithium metal in a multitude of different electrolytes. So yeah, I'm happy to take any questions.
So we have a couple of questions in the chat. The first one being, this was towards the beginning of the presentation when it came to like the accidents and the fires from some of the different batteries. It says, does this mean that the battery storage side of renewable energy is still unreliable?
I wouldn't say that the battery storage side is unreliable. That there are lots of different batteries that you can use on the grid. You don't always have to rely on lithium ion, and having these lithium ion incidents are, you know, 1 in a million that they happen. I think the bigger issue is that they are so serious when they happen, you never want them to happen. So yeah.
And this one, I believe it was in regards to like slide 12 to 13.
Okay.
It says, when those experiments, at what duration were the tests being done?
Let me go to slide 13. Maybe this one. Okay, so these experiments, these were done at polarization of 1 milliamp per centimeter squared for 2 hours. So we were just depositing for 2 hours.
Okay, and then this is a few slides forward, but in regard to ether, does that increase polarization during these tests?
It depends on the electrolyte. By increased polarization, I think that means increased overpotential. I don't think the overpotentials are increased so substantially. I think the overpotentials are similar to carbonates, where the overpotential for the current densities that we're running are about 0.1. It may be a different scenario if you use a higher current density, for sure.
Okay, and then for slide 23, it says, why doesn't the spectral resolution discern the different peaks?
Okay, so this one. So it's because of an NMR property for lithium-7. So lithium-7 is very naturally abundant. So it's about 93% abundant, which means that in any lithium compound that you have, you're going to have lots of other lithium atoms around. That means that those lithium nuclei can couple with nearby lithium nuclei, and that causes broadening and smearing out in the spectrum. What you could do is measure lithium-6, where you have more spin dilution and get better resolution, but it's a lower sensitivity nucleus, so there's trade-offs there.
Okay, and then on the next slide, it says, what's the name of the spectroscopy used?
This is called exchange spectroscopy.
Okay, and then another question says, has simulation been able to replicate the behavior observed in your experiment?
We have not. If you're referring to the deposition itself, we haven't done any like mesoscale modeling of the deposition behavior. We have done density functional theory calculations looking at the electrolyte decomposition at the lithium electrolyte interface, and they do match the trends that we see in SEI formation and electrolyte decomposition that we get with NMR.
I don't see any other questions yet, but if anyone has any other ones, you still have a bit of time. You can just put them in the chat and I'll look for that. Okay, I don't see any other questions, but for Professor Marbella, maybe you just want to end with talking about maybe next steps you see with your lab or the different experiments, anything new maybe coming out soon that you're working on?
Yeah, so something that we actually just published, I think it'll be online soon, is so we're continuing to work on lithium metal. We're starting to do some of these experiments in situ. So how can we monitor lithium deposition simultaneously with electrolyte decomposition? But what we have specifically coming out in, I think, the next week or so is some characterization of the other side of the battery. So how do these analogous processes occur on the cathode side, where you have, so what goes on the anode side is mostly electrolyte reduction, and on the cathode side you have electrolyte oxidation. So how are these processes similar? How are they different? We actually see that these two sides can talk to each other. So things that form and deposit here can actually be passed back and forth between these two electrodes during electrochemical cycling. So that's something that we'll have online in the next couple of days.